All right, so let's go ahead and look at questions on the homework. I think maybe we'll try to keep it a little bit organized and start in section 1.1. Does anybody have questions that you want to take a look at? I don't think I have anything from 1.1 on my list of questions that people asked me that I want to make sure I cover, but there's certainly some things in here worth looking at. So is there anything out of 1.1 that somebody wants to go through in detail? So with composition, the function stuff, some of this is, maybe a quick answer. Some of this takes a little longer. Last call for section 1.1. Well, here, maybe we'll go through this one. This one was the one that I know that I think at least two people asked me about an email. So we don't have formulas for functions f and g. What we have is a table of values, and we want to figure out some composition stuff. So let's see what we can figure out. So just, filling out values, if I start here at x equals -7, find f composed with g of x. So I want f composed with g, and when x is -7, I'll plug in -7. And the way the composition works is that I take the function on the right and I'm plugging it into the other function. Okay, so I want f of g of -7. If I look at my chart, g of x is -4 when x is -7. So if I plug -7 in for x, my output will be -4. So what I'm going to do is have f of -4. So then I say, well, is that a value that I know? So I look at my x values. Here's -4. When I plug that into my f function, I get -3. Okay, so f composed with g of x is -3. Okay, so moving on down the line, when x is -4, find g composed with f of x. So I want g composed with f when x is -4. So that's g with the f function plugged in. So I'm taking f of -4. I'll say, all right, here's -4. When I plug that into f, I get -3. So I need to know what f of -3 is. And that's one of the things I don't know yet. So I say, well, I'm going to have to hold off on responding to this piece until I find the answer to this piece. Okay, so these two are going to be the same. So then I say, well, how do I find f of -3? I need to use some piece of information that I already know. Okay. So what I'm going to do is I'm going to say, well, in order to find f of -3, I need to use something about f that I know. If I just look at the f function, f of -7, f of -4, f of 11, those aren't the right things. I want to find f where I plug in -3. So what I'm going to do is I'm going to take this composition, f composed with g, and I'm going to just look at what we would get for these different things, right? So f composed with g, when I plug in -4, equals 11. Let's just see if this is helpful at all. What does this look like? I already have the answer, but let me just see what information it gives me. So this means that when I plug in g of -4, I'll put 11. G of -4, if I look at my g function, when I put in -4, that puts in -3. So that's telling me that f of -3 is 11. That's exactly what I need. Okay. So that means that f of -3 is 11, and then back here, that's what we got. G composed with f of -4 was f of -3, and that's now 11. So that gave us two more answers there. Okay. What's f composed with g? I'll look at this box, so I want to plug -3 in. So I'm taking the f function and I'm plugging in g of -3. G of -3 is 11. So this is now equal to f of 11. So I go to x equals 11, f of 11 is negative 4. Okay. Next, g of 11. So I need to figure that out, and once again I need to take advantage of some other information that I have. Okay, so obviously other things where I'm plugging into g of negative 7, negative 4, negative 3, that's not helpful here. I need to say, how do I plug 11 into the g function? So what I'm going to do is I'm going to look at the composition where I'm plugging the f function into g. So let's look at g composed with f and say, all right, when I plug in negative 7, what happens? And I have g of f of negative 7. When I plug negative 7 in for x, f is negative 7. This is g of negative 7, which is not helpful because I want to find g of 11. So g of negative 7 is not helpful. Okay, so then I'm going to try something else that I know. G composed with f, right? I know it's, when I plug in negative 3, I get negative 7. So let's try this out. Plug negative 3 in for x and see what I get. So the negative 3 first goes into the f function. F, when I plug in negative 3, is 11. So f of negative 3 is 11. And so now I'm looking at a g of 11. And I know that g composed with f, right, when I plug negative 3 in for x, gives me 7. So that tells me that g of 11 is equal to 7. And that's what this is g of 11. So I know that that's equal to 7. Okay, so then we just have one more here, g composed with f, where I'm plugging in 11. So that's g of f of 11. F of 11 is negative 4. So I replace the f of 11 with negative 4. G of negative 4, here's negative 4. G of negative 4 is negative 3. Okay, some key things to keep in mind with composition. When we write notation like this, that does not mean multiply. Okay, that's important to keep in mind going forward. We have to be careful about what operation we're doing. Right? So if I'm talking about functions, we plug into functions. We multiply numbers. We can multiply functions, but we'll write that specially. But when I have a function like f or g, a number in parentheses next to it, that's how we write plugging into. So that's composition, not multiplication. Okay, so it's easy to get confused. The notation isn't perfect, right? So we have to be aware of our context a little bit. All right. Last call for our questions on 1.1. Okay, so let's go ahead and take a look at section 1.2 then. Question 11. Find all the zeros of this function, and it's a cubic function, okay? And that can be a little bit tough. So we're looking at a little bit of pre-calculus stuff. This is something that you should have learned in pre-calculus or college algebra. And the key here is to see if we can find one of the zeros. Okay, and maybe to help you understand this, let's think about what would happen if I already had this thing fully factored, right? So I'm just gonna give you a little bit of review of algebra before we solve this problem. So let me do the review over here. Let's suppose that I have something factored, right? So something like x minus 5 times x plus 2. Okay. When I multiply this out, when I FOIL it out, right, the x times x gives me x squared, right, plus 2x minus 5x, and then negative 5 times negative 2 is negative 10. Okay, so when I'm done multiplying it out, if I started, with just x's, I'll have an x squared. That's really nice. But this last number here, the negative 10, it's the factors of negative 10 that I'm going to be, that are going to be my roots, okay, that I'm going to be able to use to factor. So if I have a number over here, the possible roots that I have are going to be the factors of this last number. Okay, now we didn't start with an x squared, right? We started with an x cubed, and there was a 4 in front. So let's just do one more quick multiplying out example. Let's suppose I take something like 2x plus 1 and 2x minus 3, and I FOIL that out. Right, so 2x times 2x will give me 4x squared, okay, minus 6x plus 2x and minus 3. Okay, so what do I get? I get 4x squared minus 4x minus 3. All right, here's where things get difficult. When I look at negative 3, and I say, well, what are the factors of negative 3, right? I have 1 and 3, and then negative 1 and negative 3. But one of my roots is none of those things, because I don't have a 1 in front here. Right, if I look at 2x plus 1, if we set 2x plus 1 equal to 0, subtract 1 on both sides, I then divide by what's in front of the x. Okay, so when I solve this equation, right, if I had factors equal to 0, and when I solve for what x is, I end up dividing by the thing in front of the x. So when I'm looking at possible factors, what we're going to do is we're going to look at the factors of our last number, but we divide by the factor in front of the x squared. So I'm not going to be able to jump straight to the answer and tell you what the roots are, but if I want to get what the possible roots are, I'm going to take the possible roots of negative 45 and divide by the possible roots of 4. Okay, so if I look at the possible zeros, okay, what I'm going to do is I'm going to take, what are the roots of 45, right? I could take, 1 and obviously negative 1. Okay. 2 doesn't work, but I could divide this by 3, right? And I could divide it by 5. Well, let's do one at a time. So if I divide that by 3, negative 3, okay. Doesn't divide evenly by 4, but I could divide it by 5 or by negative 5. You know what? Let me condense this. We'll just say every one of these could be a positive and negative. I'm not going to write each of those out separately because I don't want it to get confused. Okay, so I have 1, 3, 5. If I factor 45, right? Right. 5 times 9, and 9 is 3 times 3. I can say, okay, yeah, I have 1, 3, 5. I could multiply 3 and 3 and get 9. I can multiply 3 and 5 and get 15. Okay, and if I multiply them all up, I get 45. Okay, and that's all I'm going to get. Those are the factors of 45. The factors of 4, right? 4 factors into 2 times 2. Okay, but I could also have a 1, right? So 1 or 2 and 2. So I take all of these divided by 1 and I get this set. Or I could have all of these divided by 2. Or I could have them all divided by 4. So we don't really have any answers yet, but what we have is a list of all of the things that could possibly be zeros. Okay, I can't get any other rational zeros. Right? I might be able to get square roots or something, but this is it for rationals. So what I can do now is I can just say, well, let's test some of them. right? Let's plug some of them in, and I really just want to find 1. If I can find 1, then I might be in good shape. Okay. So let's see if we can find a 0. So what I'm going to do is I'm going to use guess and check. And what I want to do is show you how to do that somewhat efficiently. Okay. So here's my calculator. And if I want to plug into my calculator, especially if I want to test the same thing over and over again, I'm going to put this equation in as a function. So I'm going to hit y equals, and I'm going to type that in. Right? So 4x cubed plus 4x squared minus 33x minus 45. Okay, now I can quit out, and now that's stored under y1, right? So if I hit variables, and I go over to y variables, I have that function, y1, that's my function that I just entered. So if I want to enter in a number like 1, I can just use function notation, y1 of 1. I get negative 70. Say, OK, go back and try negative 1. Okay, say, nope. All right. So go back and try positive 3. Oh, positive 3 is a root. So I could say, all right, 3 works, and that's one of them. Okay. So one of my roots is 3. Now there's 2 ways that we can go from here. We can continue along with guess and check and find the rest of them. Or because 3 is a root, I know that means that x minus 3 is a factor. Okay, so what I could do is I could just take this whole thing and divide it by x minus 3. Then I need to know how to do long division of polynomials. Okay, and if you remember how to do that, that's probably the best way to go from here, because then I'll get down to a quadratic and I can keep going. If I don't know long division of polynomials, I can just continue on with my guess and check, because these are all my possible numbers. But it's kind of a big list. Okay. All right. So from here, if I wanted to try long division, okay, what I could do is say, all right, I have x minus 3. Now when I say long division, if you remember long division, there's a good chance you remember synthetic division, and that goes significantly faster. But maybe it's harder to remember, I don't know. Okay, here's how long division goes. How many times does x go into 4x cubed? Or another way to phrase that is, what can I multiply x by to get 4x cubed? I multiply by 4x squared. Then I do that, I take 4x squared times this term here. So 4x squared times x gives me 4x cubed. 4x squared times negative 3 gives me negative 12x squared. Then I subtract or change the signs. I should get a leading 0. 4x squared plus 12x squared gives me 16x squared. Now I repeat the process. What do I multiply x by to get 16x squared? I multiply by 16x. So then I do the multiplication. 16x times x gives me 16x squared. 16x times negative 3 gives me negative 48x. Change the signs and add down. So here I get 0. Negative 3x plus 48 gives me a 45x. What do I multiply x by to get 45x? I multiply by 45. I feel like I made a mistake here. Oh, yes, I wrote a minus 3x. It's minus 33x. Thank you. Okay, so let's just back that up a little bit. Okay, might have backed up a little too far, but that's okay. So we had 16x times x gives me 16x squared, and then 16x times negative 3 gave me a negative 48x, and then I changed the sign, so negative, and this became positive. So now we have 48x plus a negative 33x gives me a positive 15x. Okay, what do I multiply x by to get 15x? I have to multiply by a positive 15. So then I'll get 15x. 15 times negative 3 is negative 45. Change the signs and add, and I get no remainder, so it factors evenly. Okay, so our function f of x we can now write as x minus 3 times 4x squared plus 16x plus 15. Okay, so now I have factored out the x minus 3. And now on this piece, because it's a quadratic, if I want to break that up, I can either look at how it factors, or if I don't know how it factors, I can use the quadratic formula. Okay, so you can go ahead and factor that, or if you're like, oh, the negative 4, so the 4 in front messes me up and I don't know how to factor it, then just use the quadratic formula. Okay, so we get negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. All right. 16 squared gives me 256. I have minus 4 times 4 times 15, which is 240. 256 minus 240 is 16. Square root of 16 is 4. So I would get x equals negative 16 plus 4 over 8. And x equals negative 16 minus 4 over 8. When I add them, I'll have negative 12 over 8. Okay, which when I reduce my factors a little bit, pull a 4 out of the top and bottom, I'll get negative 3/2. Okay, negative 16 minus negative 4 is negative 20 over 8. Again, pulling a 4 out of the top and bottom, we'll get negative 5/2. The way that I write these as a factor, if negative 3/2 is a 0, then I could say x minus 3/2 works. Okay, or if I multiplied it by 2, that would be like a 2x minus 3. Okay, now I can see I have a 4x squared here. If I do the same thing with this one, right, x minus 5/2 gives me a 0. But if I threw a factor of 2 in there, that would also work, right? So I could have like a 2x minus 5. Okay, so I think that this one is actually going to factor into 2x minus 3 times 2x minus 5. And then those multiplied up give me the 4x squared, so things line up neatly. Okay, I didn't really need to factor that all the way. I just sort of did that as an exercise because it asked me for the zeros. So my zeros are 3, negative 3/2, and negative 5/2. All right. Any other more questions you guys want to take a look at? On 1.2. So some graphing and stuff, some piecewise functions. Finding the formulas for the pieces of a piecewise function. That's actually pretty important. Anything else? If not, we can jump on to 1.3. And let's look at questions there. Oh, you said, could you do that one? All right, let me go back and see if I can find which one is that one. This is the piecewise function, I think. Is that... Okay, is this the one that you wanted to take a look at? Okay. All right. Here we have a graph of a piecewise defined function. And when we look at piecewise functions, the key thing to keep in mind is that it's divided up by x values, right, in the domain. So when I look at this graph, I can see that the formula changes at -1 and it changes at 3. So when I look at the way that I'm given my function f of x equals, it's saying, oh, I have x values where I go from -6 to -1. At -1, it changes formulas, and then it goes to 3. At 3, it changes formulas again. So that kind of lines up with my experience. What I want to do is find what is the function of this piece of the graph, right, for each of the 3 different pieces. Okay, so let's look at piece 1. All right, and what I need to do is find some information for that piece, right? So I have a point, right, this far right point. When x is -1, y is 5. So I have a point on the graph. And what I'd really like to do is have another point on the graph so I can find an equation. And I think that I do, right? So here, it looks like it hits -3 exactly. So this would be -3, 0. And once I have 2 points, because I can see that it's a line, I can find the equation of the line. So first we start with slope. Okay, so I look at the change in y's, so 5 minus 0 over -1 minus -3. 5 minus 0 is 5. -1 minus a -3 is the same as -1 plus 3, which is 2. So my slope is 5/2. Okay, and then I can pick either one of these 2 points, and what I'm going to do is I'm going to plug into the point-slope equation of a line. The way that point-slope equation goes is y minus y1 equals m times x minus x1. Let me just do a quick side note. Since we're reviewing, it's helpful to form connections. If I think of my slope formula, what it's doing is it's saying the slope is y2 minus y1 over x2 minus x1, but the slope is the same between any 2 points on the line. So I could say, well, what if I call any point on the line x comma y, I could think of my x2, y2 as being just x comma y. Okay. Now, to get rid of a fraction, I just multiply both sides by x minus x1. This is the point-slope equation of a line. All the point-slope equation of a line is the slope formula, where one of my points, instead of being a definite point, is a variable point, x comma y, and then we write it without a fraction. Okay, so that's just a little bit of review. Now I'm going to go to my point-slope equation, leave my x and y, but plug in a number for x1, y1. So I can just pick any one of my 2 points, right? So I'll pick -3, 0. And I know my slope is 5/2, so I'll plug that in. So y equals 5/2 times x plus 3. And distribute the 5/2, I get y equals 5/2 x plus 15/2. So that's the formula for this piece of the line, and the domain for this is, going to go from -6 to -1. Okay. Right, so that's that piece. Now we look at the second piece. So let's look at piece 2. I could do the same process here, but I'm going to shortcut it a little bit because this is a perfectly horizontal line. The y value is always 4. So if I want to say what is the output, well, if I'm on this piece, I'm always going to output a y value of 4. So that's it. All right. And then when I go to the last piece, watch, piece 3, here I need 2 points. This first point isn't really on the graph, but I kind of run right into it, so I'm going to use it anyway. Right, so this is -3, 3. And this one is 6, and then it's, well, it's not perfect, but it looks like about -1.5. Okay, or if you want, we could say, well, it looks like it does hit this one exactly, right? So maybe I'll use this point instead, 5, 0. Okay, but I just picked 2 of the points to find the slope. Right, so I'll use 5, 0 and -3, 3. So I look at the difference of the y's, 3 minus 0, over the difference of the x's, -3 minus 5. So I get -3/8. Oh, I messed up here. I wrote this as -3, but it's not. +3. X is 3, y is 3. Okay, so 3 minus 5 gives me a -2. So we have -3/2 as our slope. Okay, and then I use my point slope formula, y minus y1 equals the slope times x minus x1. So y equals -3/2 x minus a negative, so plus 15/2. Okay, these 15/2 being the same is completely coincidence. There's nothing, no connection there. Okay, any questions on this one? All right. Anything else from this section? Okay, let's go on to 1.3 then, the trig stuff. There should be plenty of questions about trig. And one of the early things that we're working in here is you've got degrees, converting to radians, going back and forth. One of the things that is going to be important going forward, when we work with angles, most people prefer to use radians because the numbers feel really nice, right? Like, if I want a 30-degree angle, that's okay, 30 degrees, that's easy to write down and think about. In radians, pi/6 is a weird number, right? Like we write it as pi/6, but if I write out the decimals, it's this crazy thing, and it's kind of hard. So we I don't really like writing angles in radians, except that when we're doing calculus, it works out that we always want to have our functions defined using radians instead of degrees, and we'll talk about why that is when we get to the calculus part. But there's a reason for it, and so that's why we want to be able to convert between the two and be comfortable with them. All right, so having said that, is there any questions in here that we want to take a look at? There's all sorts of stuff, graphing, period, phase shift, amplitude is more graphing. Solving equations. Solving equations is probably going to be the most important thing in this section because it's out of the stuff that we do with trig later on in this class, this is going to be the main thing, right? How do I solve equations? All right, so if nobody's going to say anything, I'm going to go ahead and just review solving equations for a couple of these. We'll start with this with a sine one. We'll do a sine one, a cosine one, and a tangent one. So let me first, just sort of write this down. We have 2 sine of theta equals negative root 2. Okay. When I solve an equation and I have x's, I typically want to get it down to just x, so I get everything else away, right? So if I'm solving for theta, it's the same idea, right? So I'm going to divide by 2. Okay, and let me just give you a little bit of a review here. In algebra, if I'm solving and I don't have just an x, but I have a function of x, I need to get rid of that function. Let me give you just give you kind of an analogy. If I have x squared equals 4, the way to solve for x is to get rid of the squared function using its inverse. And the inverse of a squared function is a square root function, right? So you can think of square rooting both sides, right? So I get x is the square root of 4. Except that the square root of 4 is 2, and that's not the only answer. I also get x equals negative square root of 4, right? We take plus and minus. And why do I do that? Well, if I, think about the graph of y equals x squared, okay, if I say that graph equals 4, then what I'm doing is I'm saying, well, I want to find out where does that graph give me an output of 4. Outputs are y values. So I want to say, where does this graph have an output or a y value of 4? And there are 2 spots, right? So 2 different x values will give me that answer. When I look at a square root, I only get one number, but my original problem had 2 answers. Okay, so I want to make sure I recover them both, and that's why we use the plus and the minus with a squared. Okay, we have a similar thing with trig functions, and after all the previous problems, you just did some graphing. So I know that the graph of y equals sine x, looks like this. So if I say, all right, pick a number, and I want to solve sine of x or sine of theta equals that number, right? In this case, negative root 2 over 2. Okay. I want you to notice that we're going to run into infinitely many points. Now, this says solve it on the interval 0 to 2 pi. That's going to be 1 period. So then I can see I have 2 different points that I hit there. So I know I'm going to get 2 solutions in the 0 to 2 pi domain. Okay, if I allow my domain to be all numbers, then I get infinitely many solutions. Okay, I want to make sure that I can find them all. All right, so here's how we do this. Rather than looking at the graph like y equals sine of x, I think it might be better to look at the unit circle. Okay. The way that I can connect angles to trig functions is if I take a point on the unit circle, okay, I have a point x comma y, then going from the origin to that point forms an angle theta. The x value gives me cosine theta, and the y value gives me sine theta. We're going backwards. I know what I want sine of theta to be. I want it to be negative root 2 over 2. So what I want to do is say, well, I know sine theta is a y value, so I'm going to find out what angles give me that y value of negative root 2 over 2. So this is a y value of negative root 2 over 2. And I'm going to get these two angles. And they're going to be symmetric. So if I can find one angle, I can get the other one. It's going to be the same angle off of the horizontal, but going to the left. Okay. So the way that I find the first one, we can either write this as sine inverse. If it's one of my special angles that I remember from trigonometry, I might be able to just write it down. And I know that if I had a 45-degree angle, sine of 45 degrees is root 2 over 2, right? Or in radians, that's pi over 4. Okay. To get a negative, I'm just going to put in a negative angle, right? So I'm going to have negative pi over 4. Now, negative pi over 4 isn't in my correct range, right? What I did is I solved for and got this answer over here. But if I move over by a full period, I'll get this one over here. So I could also get a solution by adding 2 pi to it. 2 pi is 8 pi over 4. So negative pi plus 8 pi is 7 pi. Okay, so that gives me one of my solutions. And what we did is we said once you have one of your thetas, to get the other one, what I'm going to do is I'm going to take pi minus the first answer. Okay, so if I take pi minus negative pi over 4, that's pi plus pi over 4. Okay, which is 4 pi over 4 plus pi over 4. Or 5 pi over 4. Okay. That's also between 0 and 2 pi, so that's another solution I want. Okay, and I should just get 2. I know from my graph I'll get 2 answers in the 0 to 2 pi range. Okay, so these two are it. So that's what I would type in here. Now, if I wanted to write down all infinitely many possibilities, right, so we'll just solve this problem first, right? I have 5 pi over 4, comma, 7 pi over 4. Okay. To get all infinitely many, and that's not what this question is asking, but since we're reviewing, I just want to review that. What I want to do is I want to take these two, different unique angles and just say, well, I could always shift over by a full period, right, by 2 pi. So we could have 7 pi over 4 plus a multiple of 2 pi. And the way I write a multiple is I'll just write times by something, right? We'll pick k. So 2 pi times k, or 2k pi. Or I could have 5 pi over 4 plus 2k pi, where k is any integer. Okay, so when I have a sine function and I'm solving, I can get one answer either because it's a special angle, or if it's not a special angle, I type into my calculator and I get my inverse sine value, and that gives me 1. And then we take pi minus that to get the second unique angle. Okay, and then we might have to shift over by a full period, but the pi minus is because of that symmetry, that left-right symmetry. Okay, so solving sine of x equals a, I get x equals inverse sine of a, and x equals pi minus that same number. Right, and then you can add the 2k pi depending on what kind of question you have. All right, does that make sense? Any questions on that sine function? Okay, so now what I want to do is I want to go on and basically go through the same thing except for cosine. Oh, that's not a cosine. Here's a cosine one. Okay, I want to do the same thing, but I want to solve for cosine. Okay, so we go through the same process to begin with. I want to get the cosine function by itself, so I add 1, then divide by 2. Okay, and then I'm going to do the same thing initially where I say, okay, I need to get rid of cosine. I use the inverse. Is there a special angle that gives me 1/2? And the answer is yes. If no, then I just type it in my calculator. Okay, the special angle that gives me 1/2 in the cosine is 60 degrees, or pi over 3. Okay. Look at the unit circle again. So we said before that when I have point on the unit circle, the y value is sine of an angle. The x value is cosine of an angle. So if I have cosine x equals 1/2, then I'm looking for an x value on my unit circle that is 1/2. Okay, so I get this point here and then this point down here. So there's my angle theta that we found was pi over 3, or 60 degrees. Here I don't have left-right symmetry, I have up-down symmetry. Okay, so to get my second angle, I can just, instead of going up by that amount, I go down by that amount. So instead of an angle of 60 degrees, I can think of it an angle of negative 60 degrees, or negative pi over 3. So my second answer, I don't do pi minus this one, I just take the negative of that one. Okay. If I was looking for all infinitely many solutions, I could write the plus 2k pi on there. In this case, if I just want the ones between 0 and 2 pi, I would say, well, pi over 3 is between 0 and 2 pi. So that's one of them. To find the other one, negative pi over 3 doesn't fit. So when k is 0, that's no good. So I'll move over by a full period. So I'll say, well, when k is 1, I'll add 2 pi, which is 6 pi over 3. So 6 pi over 3 minus pi over 3 is 5 pi over 3. So those are my two answers that are in a 0 to 2 pi domain. Okay, any questions on that one? So when solving a sine equation, I get my first answer. The second answer is pi minus the first one. For cosine, after I get my first answer, I just take 0 minus the first answer, or just take the negative of the first answer. Okay, now I don't think that there was an example on the homework of this, but while we're reviewing trig equations, I'm just going to go ahead and write an example where we solve a tangent equation. Okay. And I'm going to do two things here. First of all, I'm going to solve the tangent equation, and secondly, I'm going to show you what to do if your number doesn't come out to a special angle, right? So tangent x equals like 1 or √3, you could solve using the knowledge that you have from your trig class. But tangent x equals 5 is not a nice angle that we can just write down, so it's not going to work out neatly. Okay, so here's how tangent works. The graph of tangent doesn't have a period of 2 pi, it has a period of pi, and then it repeats itself. So when we solve a tangent function, I don't have to worry about a second answer in the 0 to 2 pi range. I get one unique answer in the 0 to pi range, and then a second one in the pi to 2 pi. All right, or actually the graph more neatly fits into a negative pi over 2 to pi over 2 domain. It has these asymptotes. Okay, if you recall. And then it repeats itself. Okay, so the way that I solve tangent is I'm just going to use the inverse tangent. So I take tangent inverse of both sides. So tangent inverse of tangent of x is just x. And to find tangent inverse of 5, what I'm going to do is I'm just going to go to my calculator. And above sine, cosine, and tangent are their inverses. So there's tangent inverse. So I just hit second to get to tangent inverse, plug in 5, and it'll give me a number. Now I'm in radians, so that gives me a radian number. If my calculator was in degrees, then I get a different answer in degrees, right? So 78.7 degrees, or 1.373 in radians. And then if I want all infinitely many answers, I just take every multiple of pi, because I can see, oh yeah, if you pick like a y value to hit here, I'm only going to hit once no matter what. So I just get one solution, and then it repeats itself every pi. So in a sense, tangent is actually simpler than either sine or cosine. I don't have to worry about a second solution. I just throw that k pi on. Would your calculator have to be in degrees or radians? That depends on the question. In a question like this, they don't explicitly tell you whether or not you should be defined in terms of degrees or radians. They give you a little bit of a hint because the domain 0 to 2 pi is exactly a circle if we're talking about radians, and it's like not anything significant when we talk about degrees, okay? So it's maybe a little implied that it's radians. In general, though, what we want to do is we want to always think about our trig functions being defined in terms of radians unless the problem says otherwise. Okay, so unless we have some other context that say that this is degrees, my advice would be to always just leave your calculator in the radian mode and use that. Once we get to the calculus stuff, we're always going to use radians because our derivatives are going to be defined using that way. Or we're going to figure them out where the trig functions are defined using radians. All right, any other questions from 1.3? Question 20. All right, so this question is a little bit more complicated because I've got like sines and sine squareds and stuff going on. And what I want to do here is I want to break this down into pieces, right? So in the last problem, the way that I solved a sine function, an equation with a sine function in it, was to get the sine by itself. And I want to do that same thing here. That's just going to be a little bit more work to do that first step. So if I have 2 sine squared t plus sine of t minus 1 equals 0, what I want to do is get sine of t by itself. One way to do that, I think maybe a helpful way to think about that, is if I do a substitution. If I say, okay, let's just pick a different variable, right? Maybe let y equal sine of t. So then this would look like 2y squared plus y minus 1 equals 0. And if I tell you get y by itself, then I think that you know how to proceed. You're like, oh, that's a quadratic. I can either factor that or I can use the quadratic formula to solve for y. So let's go ahead and do that. Let's see if we can factor this to solve for y. So I need a 2y and a y to multiply and get 2y squared. I need a 1 and a negative 1 to multiply and get a negative 1. So we'll just guess and then see if we could have to fix it. So 2y times y is 2y squared. 2y times negative 1 is negative 2y plus y will give me a negative y. That's no good. So I say, okay, I need to make a change. So let's go ahead and try minus and plus. Okay, so 2y times y gives me a 2y squared, good. 2y times 1 is plus 2y. Negative 1 times y is minus y. Those add up to y, good. Negative 1 times 1 is negative 1. That checks out, good. So that's how it factors. So I have 2y minus 1 equals 0 and y plus 1 equals 0. So add 1 and divide by 2. Subtract 1. So now I have solved for y. Now I go back and I say, okay, replace that back with sine of t. So now I'm back in the same situation as we were in the last question, where I'm solving a trig function equal to a number. Okay, I'm just going to do it as two completely separate problems, right? So for my first one, I say, all right, use that inverse. Okay, now again, if you remember your trig stuff, you should remember what angle you plug into sine to get 1/2. Should remember and do remember are not the same thing. So for those of you who do remember, then you can just write down the angle and you're good to go, right? 30 degrees, or in radians, it's pi over 6. If you don't remember, here's what you can do. You can say, oh, I got to take the sine inverse of 1/2. I'm going to use my calculator. Sine inverse of 1/2. I'm in radians. It spits out a terrible decimal. I'm like, oh man. Here's the thing. I have a good feeling that this is going to be some fraction of pi. So if I divide out the pi, then I get a fraction of pi. And you might recognize that fraction, or you can hit convert and say, oh, that's 1/6 pi, right? So when I take sine inverse of 1/2, even if I didn't remember it, I can use my calculator to get that exact answer and get 1/6 of pi, or pi over 6. So that's one solution. And then I take pi minus that to get the other. So pi minus pi over 6 is 5 pi over 6. Okay. So I get pi over 6, and I got 5 pi over 6. All right. Now, as a, almost completely separate problem, we solve sine of t equals -1. So I could try sine inverse of -1, or if I just think about the unit circle, the y value is going to be -1 when I'm pointed straight down, or an angle of 3 pi over 2. Okay. When I look at the unit circle, I'm like, there shouldn't be a second value. And when I try it, when I take pi minus 3 pi over 2, I get negative pi over 2. That's not between 0 and 2 pi. So if I add 2 pi to it, I'm going to get negative pi over 2 plus 4 pi over 2 gives me 3 pi over 2. Back to the same spot. Okay, because there's just one answer here. Okay, so those are my 3 solutions. So, I guess even more generally, anytime you have a complicated trig equation, you can always just think of the trig functions as being pieces. And if you want, you can even do a substitution, replace them with something like a y. And that makes it easier to do the algebra bit, right? In this case, factoring. All right, any other questions on this section? Okay, how about 1.4, inverse functions? I want to make sure we have time for exponentials and logs. So if nobody has a question on inverses, I'm just going to skip straight to 1.5 because I think that's the more challenging section. Okay, let's look at 1.5. Oh, we still have a little bit of time here. What time do we go to? 12:15? Okay, so we have time for a couple problems. All right, is there anything in 1.5 that you want to direct at? I mean, I'm definitely going to do some examples, but I want to do the ones that are bothering you first. 19 and 21. Okay, solve exactly. Log base 3 of negative 2x equals log base 3 of 2. The way that I'm going to solve a log equation, right, where I have x's inside the logs, is to get rid of the logs, okay? And I'm going to get rid of them with an inverse. So just like if I had like square root of negative 2x equals the square root of 2, you would say, oh, I get rid of the square roots by squaring both sides, because that's the inverse. So I'm going to do the same thing here. I'm going to use the inverse function. The inverse of a log is an exponential that has the same base, right? So I'm going to use an exponential base 3. So I take 3 to the power of log base 3 of negative 2x, and that's equal to 3 to the power of log base 3 of 2. And the exponentials and the logs wipe each other out, just like squareds and square roots wipe each other out. So we get negative 2x equals 2, okay? And when I divide, I get x equals negative 1. And that's my answer. Okay, let me try, make sure this still wasn't just a... Yeah, so I think for all of these, since the bases are the same, right, my exponential I can use to just wipe out the log function and just set the insides equal to each other. Okay. And 21, we're doing something similar, except that I don't have an exponential on one of the sides. Okay, so that makes it a little bit more challenging. But I'm going to use the same process. I want to wipe out the log using the exponential. So I'm going to start with log base 6 of negative x squared minus 20x equals 2. I'm going to use the exponential base 6 on both sides. So I have 6 to the power of log base 6 equals 6 to the power of 2. On the left, the exponential and log wipe each other out, and I just get the inside function. So negative x squared minus 20x. On the right, I have 6 squared. That's just 36. Okay. And so now I say, oh, okay, I have a quadratic. Let's just go ahead and solve a quadratic. So I'm going to add x squared to both sides, add 20x to both sides. Okay. And then we can factor and solve. Now, I do want to take this one through because I want to show you something that is something we have to be careful of. So let's go ahead and factor this. 20 by 12. I'm blanking out. Okay, I think 2 and 18 work. They have to both be positive because I'm adding up to I'm multiplying to a positive 36, so they're both positive or both negative, and they add up to a positive, so I got to start with positive. So I think this works. So x squared, 2 times x gives me 2x, plus 18x gives me 20x, and then 2 times 18 gives me 36. Okay. So I get x equals negative 2 and x equals negative 18. What I want to do when I get answers, especially if I ended up with a quadratic, is I want to double check and make sure that those answers work. Sometimes you can get a false answer. Okay. Now, it typically happens when you do things like square both sides, but it's a good idea to just always double check anyway. Okay, so in this case, I think they're both going to work, but we want to check them. So what I'm going to do is I'm going to plug negative 2 in for x and see what happens. So if I plug in negative 2, I'm going to get the opposite of negative 2 squared minus 20 times negative 2. Okay, and I get 36. So I'm taking the log base 6 of 36. And maybe I don't know what log base 6 of 36 is, but I can plug that in and that makes sense. Okay, so I try the same thing again with negative 18. So I take negative 18 squared minus, 20 times negative 18. And I get the same 36. So I'm like, oh, okay, both of those give me the same input into the log, and I think that that's going to be right. If I got log base 6 of a negative number, that's no good because I can only put positives into a logarithm. Okay, so those are my two answers. All right. Any other questions out of this section that you want to take a look at? '22 is rough. Well, why don't we take a look at it then? Let's look at question 22. Solved exactly. I have log base 64, and I have two of these logarithms. One of the things that I need to be careful with, remember we said the way we get rid of a log is using its inverse, it's exponential. If I had something like the square root of x plus 2 equals 5, and I squared both sides, I don't get x plus 4 equals 25. I'm not taking each thing that I see and squaring it. I'm taking each side of the equation and squaring it. So on the left, I would have to FOIL things out. Okay, so it would turn into this, which didn't actually work. I actually didn't get rid of my square roots when I squared both sides. Okay, so that didn't help. So we have to be a little bit careful with square roots and squareds. We have to be just as careful with logs and exponentials. If I want to square both sides and get rid of a square root, I want to have just the square root on one side. If I want to get rid of a logarithm, I want to have just that logarithm on one side. Okay, so what I want to do is first get rid of this 1/3. So let's just write our problem here. So the first thing I'm going to do is add 1/3 to both sides. Right, for the same reason that, when you leave a piece on and you square both sides, it messes everything up. With logarithms and exponentials, it's just as bad. Okay, so I get rid of the 1/3 by adding it to both sides. Then what I want to do is I want to say, well, I want to have just one logarithm. Can I combine these together? So what I'm going to use is I'm going to use properties of logs. And one of the properties is if you have log base b of a plus log base b of we'll use x and y. Log base b of x plus log base b of y. When I'm adding logarithms, I can turn adding on the outside to multiplication on the inside. We get log base b of x times y. Okay. Subtraction pairs up the same way with division. So log base b of x minus log base b of y gives me log base b of x over y. Okay. And just for completeness, we'll write the third property. Log base b of x to the power of y is y times log base b of x. We won't need that one in this problem, but it's still handy, right? If I have an exponent inside a log, I can bring it out in front of the log. Okay, it's this property 2 that we're using here. I'm subtracting these two, so I'm going to combine them together into a single logarithm by dividing. So this is log base 64 of negative 5x plus 7 over negative 10x minus 6 equals 1/3. Okay. Now I have a single log equal to some number, and I can use the inverse, right? The exponential base 64. So we take 64 to the power of the left, 64 to the power of the right, and on the left, the log and the exponential wipe each other out. On the right, I have 64 to the power of 1/3. Okay, messy. See if I can get rid of that messiness somehow. Remember with exponentials that if I have a fractional exponent, the numerator is like the power and the denominator is like the root. So this is like the cubed root of 64. Okay. The cube root of 64 is just 4, right? 4 times 4 times 4 gives me 64. All right, so this is simplified a little bit. We have negative 5x plus 7 over negative 10x minus 6 equals 4. And if I want to solve this, let's get rid of the fraction. So I multiply both sides by the denominator. So we have negative 5x plus 7 equals, if I distribute the 4, negative 40x minus 24. And now we're well on our way, right? Now I can add 40x to both sides. Subtract 7 from both sides. So 40x minus 5x gives me 35x. Okay, negative 24 minus 7 will give me a negative 31, and then I divide to get x's negative 31 35ths. Okay. All right. Any questions on this one? Okay, just to give you a little bit of an idea, the stuff that we're doing in these review chapters, the point is this is stuff you should have been exposed to. We want to try and hit like a broad variety of topics because you've seen them before or should have seen them before. We're hitting a big variety and we're hitting them really quickly, right? Because you've learned it before. Okay. However, that doesn't always mean that you remember everything. So when you run into stuff that you're confused about, right? Let's suppose we're looking at these exponentials and you're like, properties of logs, man, I don't remember any of those. Well, then that's something that we want to take a look at. And we have some time, right? So starting this week, we're going to be looking at limits, and we're not jumping right into all this exponential business, okay? So you have a little bit of time to get the, your exponentials cleaned up. Now, you still want to get through the homework, right, in a timely fashion. But the idea is that you want to think of all of this review chapter as being a little bit of a diagnostic, right? The areas where, you felt really weak or you didn't understand stuff, it's something that we want to address. And the sooner that we address it, the better. And so it's stuff that we want to go back and look at or do a quick review of. You can meet with me. You can go back and look at a pre-calculus book. Look up an explanation, a quick YouTube video, or try some problems. But you want to make sure that you feel comfortable with it. The other thing that I want you to note about this review section is that some of these problems, like this one's kind of complicated. When we're solving equations, it's usually not going to be quite this complicated in the calculus problems that we're going to do. But on the other hand, the problems that we're going to do are not going to be solve this exponential equation. It's going to be solve this calculus problem, and this just comes up as a piece of it. So the questions that we do are typically going to be simpler, but they're also going to be, you kind of need to know them better, right? You need them as second nature, and that's why we go in a little bit more depth in these sections to make sure that we really stretch your pre-calculus knowledge and make sure that that's all fresh in your mind, so that when we get to the calculus problems, you're not trying to think about how to solve the algebra. You keep your attention focused on the calculus, and the algebra is just second nature. That's the idea. Okay, well, that's the theory anyway. So if you have questions with this, or there's something that you're stuck on, let me know. The sooner the better. I'm happy to go through this. We can even have like a review day if you like, right, where we set up a time and a few of you come in and we'll just go over some topics, right? So maybe some trig or some exponentials and logs or something like that, and that's fine. So just let me know where you're at on that, and we can set something up. Otherwise, homework is due tonight. Try to get it all done. If you don't get it all done, if some of it spills over, you can use a late pass. If you're having trouble, email me or hit the message my instructor button, something like that, and let me know.